everybody, it's Miss Abney. I'm here to go over topic 2, lesson 1. We're going to start now getting into kind of the vertex form and the quadratic function. Some key vocabulary that you need to know about is what a parabola is, the quadratic function, and the vertex form of a quadratic function. We also, in vertex form, you might have been introduced to the axis of symmetry, the y-intercepts, the vertex of a parabola, and the x-intercepts. So I know we've talked about the x and y-intercepts, but axis of symmetry and the vertex of the parabola should not be new vocab, but you might have forgotten them. So looking at the concepts, a function is a quadratic function if its equation can be written in the form of f of x equals ax squared plus bx plus c, with a is not equal to 0, because if a was equal to 0, then we would have a linear function. All quadratic functions are transformations of a parent function, and the parent function is x squared. Another characteristic to quadratic functions is that they typically have the domain of all real numbers, unless otherwise specified, and usually we would see that as some kind of conditions that they're being met, or they're part of a piecewise function. The graph of a quadratic function is called a parabola, and the vertex form of a quadratic function, which will come in very handy as we go on, is f of x equals ax minus h squared plus k. And h and k is going to be that vertex, or that minimum or maximum point of your parabola. So in this case, right here in this little blue dot is going to be your vertex. And the vertex is very important because it highlights, or the vertex form highlights the vertex of the graph, which makes it a little bit easier to graph this type of function. All right, let's go look into example 1, now that we've talked about some key vocabulary. All right, so how are the transformations of the graph f of x equals x squared, which is this blue graph, related to an equation representing another quadratic function? They want us to use the sliders to explore the function. Well, let's look at this function. This function is, we talked about in the last vocabulary terms, as a transformation being a x minus h squared plus k, where the h was your x value and the k was your y value for the center of your graph, for this point, like right there. In this case, we don't have a k. We're not adding or subtracting. We are multiplying by -1/2, but we are not adding or subtracting. So we're looking at an h of -2 and a k of 0, because we're adding or subtracting nothing from this equation. Notice here too how I changed the sign. This right here is a positive. Oh, this froze for a second. So as this catches up to us, this right here is a positive, and this right here is a negative. When you're finding the HK, it's a great way to think about is that this is -HK, so that this sign changes no matter what you do. So looking at our new HK, that means we go over -2, so -2, which is right here, and we don't move up or down for our vertex. It's still at 0. Then this negative right here, this negative is telling us that we are reflecting across the x-axis. And so what was pointing up, both these arrows are pointing up. Now both arrows should reflect and point down. And then this 1/2 means that we're multiplying 1/2 to each one of my points. So this is 1, 1. I'm going to multiply 1/2 to, or negative 1/2 to that. If I multiplied, that should be 1/2, 1, and so on and so on. So this is actually kind of stretching it. Actually, it's compressing it in a vertical because this is a vertical compression. So as a reminder, vertical compression is when x, or I should say a, let's keep the same format, a is less than 1, and a stretch is when a is greater than 1. I like how I say 1 and I write 0. All right, so a lot of information just on this one equation. We could figure out a lot of things just on that one equation. So the vertex form shows that there are 3 different ways in which the graph function f of x, x squared may be transformed. It could be having a vertical stretch or scale, and we could shift it over to the left or right, or shift it up and down. So the value a determines the direction of the parabola opens and whether the graph is stretched or compressed. Ours was negative and our parabola opens downward. Other ones are positive and the parabola opens upward. The value of h determines the horizontal translation. So we saw that we moved over to the left 2 points because of this 2. The value k determines the vertical translation. We don't have anything being added to our equation here, and therefore we're still when y equals 0. So the equation shows that the graph is to be translated 2 units to the left, will open downwards, and will be vertically compressed. All right, so let's go to the second part of this. How are the transformations of the graph f of x equals x squared related to the equation representing another quadratic formula or function? So I'm just going to kind of grab this right here. Okay, so this 2 is an a greater than 1, so we are looking at a vertical stretch by a factor of 2. My vertex, remember this is going to be negative h, comma k. So looking at my negative 1, negative times a negative is a positive, so that's going to be 1, comma. This one takes on the sign. Notice how there's no sign change here, so that's going to be negative 3. Which means that we are moving our graph, we are moving it right 1 unit and down 3 units. Because our original vertex is 0, 0, so our center has changed by 1 unit and negative 3 units in the both vertical and horizontal. And we can actually see that here with this graph. We can see the move over by 1 with this blue line and the translation down by 3. We can also see that the graph is kind of squeezed and it's not as wide as this one. If I look at this base right here and this base right here, the second one is a little bit wider, which means it's like a rubber band being pulled up. So the solution, the equation shows that the graph is to be translated 1 unit right, vertically stretched, and translated down 3 units. This will open upwards. When a is greater than 0, the parabola opens upwards. When a is less than 0, the parabola opens downwards. So again, if it's positive or negative in front of this a, you're going to have the parabola facing in different directions. If the absolute value is greater than 1, the graph is stretched. And if it's between 0 and 1, the graph is compressed. To see these effects easily, use the same axes and units of all graphs. All right, so here is your try it. Describe the transformation of the parent function and then graph the function. So we're looking at a negative. So what does that look like? That's a reflection across what axes? Then we're looking at a positive 2 within my squared parentheses. And then we don't actually have anything being added on the outside. So what does that really look like? The second part says, describe the transformations of the parent function, then graph the function. So again, we have nothing being multiplied to my kind of grouping of my squared numbers. But we do have this -1. How is that going to impact my h? And then we have the positive 2. How is that going to impact my k? All right, so that is the end of example 1. Again, if you guys have any questions, please get a hold of me, and we will be working on example 2 next.